Welcome to the video presentation of my master's project for the MSc CAVE. The title is Adaptive Wavefront Scheduling for Coherent CPU Path Tracing. My name is Felipe Hidalgo. Let's get to it. In terms of the problem, during research I found that as rays move through a scene, they interact with different surfaces, materials, and lights, causing them to follow increasingly different paths. In a CPU wavefront path tracer, this creates divergent workloads and reduces both execution and memory coherence, making the shading stage less efficient. Wavefront rendering already gives us cues where this work can be reordered, but there is no built-in mechanism deciding how the work should be organized or orchestrated to make it as coherent as possible. Previous approaches have used static information such as materials and textures to group similar work, but scheduling also has a cost of its own. This led to my hypothesis: could runtime information be used to better orchestrate the shading workload and improve rendering performance? So talking about hypothesis, as I was saying before, I wanted to prove that runtime information could be used to better scheduling decisions. By considering how the workload behaves while the renderer is running, I expected to improve shading performance while still maintaining good execution coherence and producing the same final image. Here we can see the rendering architecture and pipeline of my renderer project. If we go step by step quickly, we can see that the renderer starts by loading the OpenUSD scene, including the geometry, materials, transforms, and camera information. The scene is then converted into an internal representation used by the renderer, including the Embree BVH for ray traversal. Primary camera rays are generated for each pixel and placed into the ray queue. Before traversal, the queue can be reordered using Morton Z-order, grouping rays with nearby origins to improve spatial coherence during traversal. The rays are then sent to Embree, which performs the BVH traversal needed and returns the intersection information. The results are classified and converted into shading work, which is placed then into the shading queue. The shading queue is where the main scheduling system operates. The renderer can use 4 policies that I implemented. Naming them would be none, material, texture, or the cost-benefit scheduler developed specifically for this project. The selected policy determines how the shading work is ordered before it is processed. Cost-benefit additionally uses runtime cost information collected by the cost tracker, while its cost-aware Russian roulette can terminate paths when continuing the work that is not worthwhile. The ordered shading work is then processed through BSDF evaluation and lighting, including next event estimation and multiple importance sampling. Secondary rays are then generated from this process and returned to the ray queue. Finally, the samples are accumulated into the image, while adaptive sampling determines where additional samples are needed. This process repeats until the paths terminate or reach the maximum depth. Knowing a little bit more about the architecture and pipeline, we're gonna start with the demo. The first thing I'm gonna showcase is how to build and run this program using the CLI. I created a makefile that showcases all the different commands that we can call. For example, the first one would be make rebuild, and this compiles the project using Ninja. Also, for the UI, we need to sync the UV virtual environment, and we can do that by calling UVSync. Before running the renderer, I wanted to showcase how I created the procedurally generated USD scenes. You can just call the make command, generate stress scenes, and as you can see in the output, we're creating the different materials and textures that we will implement into the scene. For textures, I implemented ones that are incredibly high in resolution and ones that are very low. By doing this, we will have different benchmarks for the various meshes within the scene. In terms of the benchmark scenes, we have 2 of them. One of them is a dragon scene that will consume the Stanford Dragon USD files from the project root. And then the mix scene that will contain both dragons and Utah teapots. To render a specific scene, within the makefile, we can reference the render commands, for example, Cornell, and we can call it by make Cornell. This will consume the specific USD file that we have inside of the project, and it'll display all the different information specific for this scene. Once it finishes, it'll show us the material cost tracker stats, the rendered information, and the total shading time. Additionally, we can call the rendering command, for example, Cornell Dragon, and we can override our various flags, for example, samples. We can set the number of samples, and we can set also or override the policy that we want to use, for example, cost benefit. And we can run the command through the CLI as well. Once we're done with the rendering, we can take a look at the outputs that will be EXR files. Here is the one for the Cornell box that we implemented with default sampling and default policy, and the Cornell Dragon that we implemented using the cost benefit policy and a sample of 256. Another command that I want to showcase is the make preview command. This is used to call the PySide6 UI. We can also update or override certain flags that we can reference in the README file of the repository. Once we call the command, the UI will open. In the first tab, called Render, we can select the scene that we want to render, and these are located within the root or the directory of the project. We consume them and then display them in a combo box. In this case, we're going to render the material variants, same for the policies. We're going to do the cost benefit, and we click on render. The UI in this case is running separately from the renderer. When I click or start the render here, it launches the C++ as a new process. So all the heavy rendering work happens separately from the interface. While this is running, the renderer periodically saves a PNG of the current image. The UI picks up the preview, loads the pixel data, and uploads it into an OpenGL 2D texture. I'm then just displaying that texture in the OpenGL widget. So as new previews are generated, the texture gets updated and I can see the render progressing in real time. Once the shading process finishes, we call the OpenImage denoiser, and how we do it is we create a buffer with all pixel data, we send it to the library, and the result, we override those pixel values into our buffer, getting us to the denoised image. For recording the different rendering stats of this Wavefront implementation, as you can see, all the different data and values are recorded into the console log. In this case, I have a Python script that gets all this different data and maps it into a CSV output, as we can see here in results. These outputs will have the specific information of the render, which then I have another Python script that, using Matplot and Pandas, will create the graphs that we can showcase in the second tab of the UI. Once we're here in the second tab called Results, there are two ways of showing the generated graphs. One of them is to render one of the two benchmark scenes, the mixed or the dragon scene. And the second way of displaying the graphs is by refreshing and clicking this button here. In case we have the CSV files within our directory, this will show. Here we can see all the graphs that we have. The UI is adjustable so we can see the numbers better, and everything is grouped by the number of samples. Each sample group will have the different graphs, for example, the homogeneity, the pipeline, run length, shade time, and shaded hits. We're going to start with the homogeneity, and this measures how consistently the shading work is accessing the same cache line or data type. A higher value most likely means the work is similar and should have better memory locality. And as we can see at the values based on the mix and the dragon scene, both material and cost benefit have better homogeneity, meaning they both show higher memory locality while shading. The second one is the pipeline graph, and this basically breaks the render into different stages, so I can see where the time is actually being spent. The important part here is the shading time, colored in green, because that is the stage affected by the scheduling policies. So in order to understand this graph, we can take the baseline render and we can take a look at the stages, the sorting, the intersect, and the shade, and then we will have all the differences between them being positive or negative. The run length graph measures how many consecutive shading records share the same property, such as the same material. A longer run generally means similar work is being processed together for longer. So the higher, the better, basically. And again, the material aware and the cost benefit aware have multiple runs. In this case, for example, in the dragon scene, 1,560 straight hits from the rays on the same materials before changing to another. Taking a look at the shading time, this is the main performance measurement. It shows how long the shading stage takes between or for each scheduling policy. Here we can directly see whether the extra cost of scheduling is actually being recovered through faster shading. And the most important result here is the one colored in red for the cost benefit. Compared to the baseline, we can see that the shading time for the dragon scene is 10% less, and for the mixed scene is almost 8%, making the process faster. The last graph will be the shaded hits, and this shows the number of shading records processed during the render. It gives us some context for the other measurements, because we're comparing the policies while processing the same rendering workload. And this basically means that because these are very similar, we're basically saying we're rendering the same for each specific policy. Together, these graphs let me look at the scheduling policies from different angles: memory locality, where the time is really spent, how similar work is grouped, overall shading performance, and the amount of work being processed. The third and final tab would be the Compare tab. In here, I can select two rendered images and compare them directly. So let me just select the stress test dragon scene, the golden render, and compare it to the 4096 samples with the cost benefit policy. This will generate a difference heat map, as you can see, which shows where the two images differ and by how much. I can then use the mean RGB and the luminance differences to quantify those changes rather than just looking at the images visually. If those values are very small and the heat map only shows a few isolated differences, I can consider that the two renders are visually and numerically very similar. The last command that I want to showcase is the testing command. You can call it with make test. It's important to mention that throughout the development of the project, I implemented test-driven development using the Google test library for C++. Once we run the command, we can see that all 180 tests as of right now passed successfully. Overall, cost benefit was the strongest approach, reducing shading time by up to 10% compared to the baseline. The main finding was that using runtime cost information helped make better scheduling decisions than grouping work only by material or texture, while also giving the strongest coherence and memory locality. The image comparisons showed that these improvements did not meaningfully affect the final renders. There are still some limitations though, mainly the small number of benchmark scenes, the single CPU configuration, and the warm-up needed to estimate costs. For future work, I would like to test the approach on production scale scenes, improve the cost model, and explore how the same idea could work on a GPU wavefront rendering. So that will be all in terms of my master's project. I hope you find this research very interesting and valuable. And please, in case you have any questions, please reference the GitHub repository for the README and user guide files. Thank you very much.